Next, I'd like to move on and consider another objective that we might have to consider during our evaluation. I would like to look at the power and energy consumption. We know that power and energy are very closely related because energy is just the integral of power over time. We know that power and energy models are becoming increasingly important, especially due to mobile computing, because there we have to carry the energy around with us. Also, we know that the energy issues are becoming very important because we are going for higher performances, and unfortunately higher performances usually also mean that we need more power. And I mentioned this already in cases where we are working with plugged computers. We have situations where the overall power consumption is so large that we also care about the environmental issues. In the context of embedded systems, there have been a rather limited a number of attempts to model the energy consumption, and I would like to mention a few of the more prominent attempts to model the energy consumption. One of the first approaches was proposed by Tivari, who modeled the energy consumption within processors. Then somewhat later, Tanja Simonic modeled the energy consumption in systems using the values that are available from datasheets. The advantage over the first method is that in this way we can model many different components. However, unfortunately in datasheets only rough approximations, only upper bounds are included, and this means that in many cases these values are not precise enough to be considered as providing average cases. Then there was work by Margarita Jacome and her students who did measurements for fixed configurations. Unfortunately, that means that you have results for exactly those fixed configurations, but it's difficult to figure out how this could be taken into account when we have a different configuration. Then Stefan Steinke from our university proposed a mixed model which was based on both measurements and prediction. Another very prominent example is the so-called cacti tool that was proposed by Juppy, who is the cacti tool can be used to predict the energy consumption of caches. And then there is a very popular tool, it's called Watch, which is used to predict the power estimation at the architecture level without actually analyzing any information at the circuit or layout level. As a result, it is obvious that this tool has problems with its precision. So let me talk a little more in detail about the model that was proposed by Steinke and his co-workers. In this case, in our lab, we analyzed the energy consumption of a board that we had there in the lab, and the model that we used was the following. We assumed that the total energy consumption comprises an energy contribution there resulting from the transformation of electrical energy into heat in the processor, and this resulting from the use of or the execution of instructions. And also in the processor we have a contribution there resulting from the use of data, and we assume that there are also contributions in the memory. So one key extension over the earlier work of Tivari is that now we are analyzing the energy consumption both in the processor and in the memory. So in order to do this, we cut the power lines to the processor and we cut the power lines to the memories, and then we were running very long sequences of assembly language programs and tried to figure out what is the impact of certain instructions on the currents, and multiplying by the voltages we were then able to obtain power and energy consumption. As a model, we assumed the following linear model. as a model, for example, for the use of instructions in the processor. We used a linear model where we assumed that for each opcode of the instructions there is a certain minimum cost that is coursed in the processor. And there is one additional cost that is resulting from transitions from one instruction to the next. And that might depend, for example, on the instructions that are used there. Then there are contributions as a result of using certain immediate values there. A W reflects the number of ones that we have in immediate values, and then also for the immediate values we were considering the Hamming distances between adjacent immediate values. We were also considering contributions from the use of registers, both from the use of a particular register and from the use of Hamming distances between register numbers in these instructions, also from the use of values there in the register and from Hamming distances between values there in the register, and also a contribution resulting from the use of specific instruction addresses. And you see lots of parameters there, and using some kind of correlation we try to figure out what appropriate values for these parameters would be. You see, for example, one result which is displaying the importance of the Hamming distance between adjacent addresses there on the address bus. And you see that for read and write operations you have slightly different currents. You can see that the currents that we measured can be modeled as an approximation using straight lines there. So that means a linear approximation is a pretty good approximation there of the impact of the Hamming distance on the consumed current. There are some number of secondary results, like we figured out that it's not important which address bus is set to 1, so that means that all the drivers for the bus lines are the same, irrespective of which bit we are actually driving. Number of ones on the address bus is irrelevant. The cost of flipping a bit on the address bus is independent of the bit position. It's not important which data bit is set to 1. And the number of ones on the data bus has a minor effect. It has an impact of about 3% on the overall energy consumption. And the cost of flipping a bit on the data bus is independent on the bit position. So that was a attempt to model the energy where we were using real measurements. In general, we can say that real measurements are a very precise way of computing the consumed energy consumption, and that's very important if you try to figure out the impact of certain optimizations on the consumed energy consumption. In such a context, you need a very precise model of the energy consumption. On the other hand, you can also work with models, and that's for example done with the cacti model. The cacti model is implemented in a tool with the same name, and the tool allows you to experimentally create the layout of caches. So that means you're creating the layout of the tag array, creating the layout of the data array, and also the layout of the associated components. And then from this capacitances are extracted, and from the extracted capacitances you can try to figure out what is the energy consumption and what is the delay time of certain cache organizations. This can be done in a rather fast way. It can be done much faster than if you were using simulations at the electrical level. Nevertheless, we can use comparisons with simulations at the electrical level to figure out how precise the results of cacti are. And towards this goal, we can have a comparison with a simulation tool at the electrical level, that's with SPICE. And you can see from the comparison down here that for various configurations, cacti is actually providing very good results, at least for the technology for which this comparison was performed. Using cacti, we can compute the average energy consumption and also the access time for various memories. In this case, on this slide, I'm repeating a slide that was already shown in chapter 3. So we can see over here that for memories, we have an increase in the energy consumption as a function of the size of the memory. And we also have an increase of the access time as a function of the size of the memory. Using the same tool, we can also study the impact of associativity of caches. We can see that the larger the associativity of caches, the more energy we burn per access. And the reason is, of course, that we have more parallelism and that we are accessing more tags and more data values in vain. And this, of course, is increasing the energy consumption. Now, for a long time, energy models existed only for processing within the execution platforms. However, in many cases, there is a kind of question that I would call make or buy. Make or buy in this case means, should I actually perform the computations on my mobile device, or should I buy some computer time on some external server, send my data there, and then get the result back? In order to evaluate whether it would make sense to send the data to some remote server, we need to figure out how much energy is required if we would like to send the information to that external server. So therefore, some people from our university have tried to figure out how much energy is actually required for sending information to some server. So they used a setup there in their lab. They did this for WiMAX, which is an internet-based communication protocol, and they were using a WiMAX device in their lab, and they were also using a local receiver, which models a kind of a mobile device, and they were trying to analyze the energy consumption that's required for communication between the two. And in order for this to work, they were using a measurement probe, which was computing the current and also corresponding to that the energy consumed in that kind of mobile device. In this setup, the resulting energy consumption was computed, and you can see, for example, that in the idle state, there is a certain amount of energy that is required. On the average, the device is consuming 880 milliwatts. It's not a very power efficient device. It's not a real mobile phone, so it's consuming a little more than a mobile phone would consume, I think, on the average. And then you can see that there are certain reports about the channel quality where the consumed power is increasing a little. Now, if we are actually transmitting data, we can see that the power consumption is increasing on the average to 1 point something watts. We can see that in the downlink time, the energy consumption, or more precisely the power consumption, is less than a watt. But if we look at the time when the device is actually sending messages there to the base station, we have an increased power consumption. So we can see that the transmission is costing significantly increased energy consumption, but the reception is hardly causing any increased energy consumption. It's also interesting to analyze the impact of the power which is used in the mobile station. Down here in this dimension, you see the power which is used in the mobile base station. Over here in this dimension, you see the energy which is consumed per bit. And the parameter which is used here is the ratio between the time used for downlink and the time used for uplink. You see over here that for this case we have a very short amount for the uplink messages and a larger amount of time there for the downlink messages. And you can see that for sending information there to the base station, we need more energy if we have only a small amount of time available for the upload case. So you see that in this case we have an energy model. This energy model corresponds to particular parameters there for this quadratic approximation of this left part of the diagram and the linear approximation of the right part of the diagram. These parameters alpha and beta describe this approximation, and these values over here they correspond to the different ratios of the time allocated for uplinks and downlinks. So we see that the energy per bit is constant for very low transmission powers. For higher transmission powers, the required energy can be approximated by a second polynomial degree. And we can also see that significant energy can be saved if we use the smallest power that's actually available, the smallest power that still guarantees communication. In the study, the colleagues over here in the group of Christian Wiedfeld analyzed the impact of different file sizes. We can see that the larger the file sizes, the less energy we need per transmitted bit, because obviously the overhead is less. So we see that for larger file sizes we can really reduce the energy that's required per bit, but then if we have reached a certain file size, increasing the size further doesn't make any sense. So there is this area where the amount of energy that's required per bit is decreasing, and then we have this transition area, and then we have this constant area. The prediction according to this curve has been verified in the measurement in the open field instead of the measurements that earlier were based on the devices used in a closed lab. So in this case, there was a setup used on the campus of TU Dortmund, where there was a base station and there was some outdoor unit that was used for the communication. And there the energy per bit was also computed. And from this curve you can see that the real energy that is consumed was actually less than what was measured there in the lab, because obviously the devices that were used for the measurements there in the field on the campus were more power efficient than the ones that were used in the lab. So using this information we can then try to make this kind of make or buy decision. That means we can decide whether we should do some computation locally or whether we should request that computation to be done on a server. So that concludes the discussion of the energy consumption and the energy models. Next, I'd like to briefly look at another objective that we can consider for evaluating our systems, and that is the thermal behavior. We know that thermal models are becoming increasingly important since temperatures become more relevant due to the increased performance. And we know that temperatures are affecting usability and dependability. So therefore, we have to look at thermal models as well. When we do thermal modeling, we typically use a value which is called thermal conductance. Thermal conductance reflects the amount of heat which is transferred through a plate made from a particular material of area A and thickness L when the temperatures at the opposite sides differ by 1 degree Kelvin. The reciprocal thermal conductance is called thermal resistance, and it's interesting to note that in thermal modeling we can add thermal resistances up like we add electrical resistances when we consider electrical networks. Also, masses storing heat correspond to capacitors in electrical networks, and therefore thermal modeling can be done very much using the same technique that we are also using for analyzing electrical models, and therefore all the well-known models that are available, the well-known techniques that are available for solving electrical network equations can be used there as well. In order to indicate the type of results that we can achieve with this way, I'd like to show some slides. This is a slide demonstrating the temperature distribution in some cryptographic coprocessor. This cryptographic coprocessor is shielded in order to provide the required safety level. But of course, this shielding is making it very difficult to keep that processor cool. And you can see that the processor inside gets a little hot, and from this little simulation you can see which temperature you would have at the case of this shielded cryptographic processor. Also, as a second example, I'd like to demonstrate the temperature distribution that can be observed for a standard PC-like processor, on top of which we are using a very large fan. In this case, there is an additional little lid put on top of the processor. As a result, the temperatures there get a little get distributed in a somewhat different way, and over here you have the distribution of the temperatures without that metal lid. So in this way you can figure out what the impact of such a metal lid would be. So that was a very brief discussion of thermal modeling. At this point in time, I would like to summarize today's lecture. During the first part of this lecture, I talked about Thiele's real-time calculus. There we were using bounds on the number of events and input streams. We were also using bounds on available processing, on the available processing capability. And using that information, we were able to derive bounds on the number of events in the resulting output streams. We were able to derive bounds on the remaining processing capability, and also on the buffer sizes and on the resulting delays. The one example that I showed demonstrates how we can use this technique in order to traverse the design space, and in order to figure out what flexibility we actually have in the design space. And then a little more briefly, I talked about models for energy and power consumption, and finally, even more briefly, I talked about modeling the thermal behavior. This concludes today's lecture. Thank you very much.